So we're about to look at integration here in chapters 18 and 19. 18 is kind of the mechanics of integration, and 19 are some applications. We have the area under a curve. That's really what the integral will give us, the area under a curve. Now, one thing that we need to make sure that we define is what we mean when we say area under a curve, okay? When we're talking about under a curve, we're talking about between the curve and the x-axis, okay? So under means between the curve and the x-axis, okay? Now that's important to recognize because if you have part of your curve that's below the x-axis, we actually would consider the area above it and underneath the x-axis to be negative area. Okay? Now we'll get to that later, and we'll look at situations, we'll look at how to handle situations where that happens, and if we want to ignore the negative aspect of that and just get positive area for all of it. Okay, but when you're thinking under, think between the curve and the x-axis. All right? Now, obviously I already said that integration is the way that we are going to do that. However, I want to develop this concept just like we did with the derivative and understand exactly what we are doing here. Okay? I want to make sure we understand exactly what we're doing. And I want to do it the way it was originally done by approximating this area in a couple of different ways. Okay? We're going to approximate the area under the curve a couple of different ways. Two of these ways are by using what are called upper rectangles and lower rectangles. Okay? So here we have this function x squared plus 1. F of x equals x squared plus 1. And it's graphed in both of these places here. And you'll notice here on the left-hand side, we want to find the area from 1 to 4. It's the same area that you see up here, the area from x equals 1 to where x equals 4. All right? The problem is this top side of it is curved. All right? And there's no formula that we can really use here to find the area when this top edge is curved. I mean, it kind of looks like a trapezoid, but it's not a trapezoid. So we can't just use the formula for a trapezoid. Okay? So what we actually are going to do here initially is we're going to divide this into what are called the upper rectangles or lower rectangles. Upper and lower refers to as we divide this region from x equals 1 to 4 into little rectangles, we're either using the upper side, okay, of that interval. Here, this side is below this side, so in this rectangle, we're going to make it using the upper side, the higher side. Okay? Or on this side, we have the same interval from 1 to 2. However, we're going to use the side that's lower. All right? Now, as you're doing this, you can kind of anticipate what's going to happen. What's going to be the case when we approximate our area with this?
It's going to wait, with the upper?
With the upper rectangles.
It's going to be over. So it's going to be bigger than the area.
Yeah, it's going to be bigger than the area because we have these extra parts up here that we're counting.
So you just have to do upper minus lower.
Well, that's one way, that's one kind of strategy people can use to approximate here. If we do lower, we're actually missing out on part of it. So what could we do with the upper and lower to try to get a better approximation? Average them, yeah. We could find the average, and that would give us a little better approximation of the area. Okay, because look at this one here. If I have this rectangle here, notice the width of this rectangle, or we could use base times height just to clarify things here. The base of this rectangle is 1, and the height of it is what? 5, okay? On the upper rectangle, the height is 5, right?
Yeah.
So we have 2 by 5, or I'm sorry, we have 1 by 5, so the area is 5, okay? And then here, again, the base is 1. And by the way, we'll always split it into even width. So we're not going to make 1, 1 and 1, 4 and something like that. Okay? So this is 1 by, how tall is it? 10. So that area is 10. And then this one here, it's 1 by how much? 17. Okay? So our total area here ends up being 32 square units. Okay? Now, obviously, we know just by looking at this that that's too much. Okay? We know that's higher than what the actual area is supposed to be. Okay? Well, because we have 5 for this rectangle, 10 for this, and 17 for this. So you have to add those all up. We're approximating this whole thing with all 3 regions combined. Okay?
So we wouldn't use the 2 on that one because that's the marker that's over?
Yeah, that's the lower side. Okay? Over here, the rectangle has a height of 2 because these are lower rectangles. We go, here's the lower side and here's the higher side of this first region. So over here we use the higher side or the upper side to make our rectangle. Here we're using the lower side to make our rectangle.
Is the upper always the right side?
Not necessarily. If our function were decreasing, then the upper would be on the left. And it's possible to have an interval, you know, that kind of goes up and then down. So on one side of it, the uppers would be to the right. The other side, the uppers would be to the left. Okay? You just have to look at it and figure it out. Okay? Now in this case here, what would the area of that first rectangle be? 2. It's 1 by 2. And then the second rectangle would be 5. And the third one is 10. So the total area here is 17 square units. Okay?
But that's too big?
But that actually is too small. All right? Now, we could approximate by averaging. Yeah, we could average these two together. And that would give us 32 plus 17. So that's 49 divided by 2. So it would be 24.5 square units. Okay? But again, that's only an approximation. It's not an exact. Okay? So, I want us to think a little bit here. How could I get a more accurate approximation? What do you think? What? Well, that's how we'll get the exact one, but we're approximating here. So how could I get a better approximation? What are some ideas? Wait, what are you saying? Okay, we have 2 ideas here. One would be to find kind of the middle, and those are the middle rectangles. That's a third option here. I'm not going to do that whole option, but if you take a look, we can make other rectangles, but instead of going to one side or the other, we could do it with the same width, but going to wherever halfway through was. So here's 1.5. We would cross the actual function right here at where x equals 1.5. Okay? And then same thing here. Between 2 and 3, we would make the height of the rectangle whatever the function equaled at 2.5. Okay?
Top of the, where the line make it.
So here's another one. Okay, we go to wherever x is 3.5. Here's x equals 3.5. We go straight up. There it is. We're making our rectangle there. Now, what's the kind of benefit of doing it this way?
And you don't have to do the place.
What?
You don't have to do the whole thing twice.
Okay, you wouldn't have to do the upper and lower and average them. That's true.
Closer to the exact.
Why would it be closer to the exact?
You're leaving out less and or overestimating less.
Okay, we're both leaving out a little bit and we're adding a little bit, right? If you look at this here, okay, we're leaving out this piece right up here. We're leaving out this piece right up here. We're leaving out this piece right up here, okay? We're leaving those triangles out, but we're actually including parts that we shouldn't. We're including this right here, and this right here. So what's the idea?
You're really balanced.
Yeah, they'll kind of balance out. It's still only an approximation, but they'll kind of balance out. All right? Does that make sense? All right. So that's one using the middle rectangles. That's an approximation method. Another method is actually using trapezoids, okay? This is a trapezoid method. If you take AP, those of you who are juniors, if you take AP next year, you'll learn this method, okay? Here, what I would do is I'm actually going to use, instead of making the side from 1 to 2 the base, that's actually going to be the height of my trapezoid, and then the two bases are going to be f of 1 and f of 2. And you guys know the area of a trapezoid is 1/2 the sum of the bases times the height. So 1/2 times 2 plus 5, so that's 7, that's 3.5, times the height of 1, so the area of this trapezoid would be 3.5. And then I would do the same thing for this trapezoid. Okay? There's that side, okay? And then I would make another trapezoid. And as you can see, this method is actually even more precise, okay? It is still an approximation method, but it's even better than the middle triangle one, okay? So there are a number of different ways that we could do this, but let's go back to our rectangles, okay? And I want you to think about our rectangles here. Oh, grabbed the wrong thing. Okay, let's get rid of all this. How could I make this more accurate? Using this method here, how could I make it more accurate?
More rectangle.
What'd you say?
More rectangle.
What would that do for us?
If you long distance in between.
Okay, so you're saying if I take this, let's say I make double the number of rectangles, okay? So now instead of the rectangles you see, I've got that one, and then I've got another one here, okay? So here I'm making double the number of rectangles. How does that look? Does that look like this is eventually going to give me a little better approximation? Okay. Yeah, because you'll notice what's happening here is I'm actually minimizing, or at least getting less of that extra area.
Yeah.
Okay? I'm actually getting closer by not having this, or this, or this, okay? Now I still have a little bit of extra there, there, and there, but you can see how much more accurate I'm going to be just by using twice as many rectangles. So let's keep going with this thought here. What do you think that I want to do with my number of rectangles? There we are. Did you guys hear that? Get it to where we have an infinite number of rectangles. Because the more rectangles I have, the less of this extra junk that I've got, right? If I can make those half of what they are right now.
But then you have to do the area, like, by whatever you divide it, you know?
Yes.
Which is like,
Okay, so what are we doing here? Obviously, we can't make an infinite number of rectangles, but mathematically, what are we doing here?
getting the one.
We're taking a limit. We're taking a limit as the number of rectangles approaches infinity. Okay? So, I want to actually look at this closer here. We're going to let n be our number of rectangles. Okay? N is our number of rectangles. Now, I want to do this in specifically with this application, and then we'll do it in general and come up with really what our definition for an integral is. Okay? So here we have 3 rectangles. Okay? Now, how do I figure out how wide each rectangle is?
Ow, it's on the bottom.
Wait, what, Ashley? Okay, the distance between the units on the bottom. So we've got, we're going from 1 to 4 here. So I would have to do, a distance between. That's 4 minus 1, right? And then what do I need to do with that distance?
Multiply it by the height of the rectangle.
Well, hang on. We want to figure out how wide each one of these is, right? Very good. We want to divide it by the number of rectangles, which happens to be n. Okay? 3 in this case. N in general. Okay? So that's going to be the base of each rectangle. Okay? The base of each rectangle is 4 minus 1 over n.
Just for this.
Just for this, okay? We'll look at ones more in general later. Okay? Now, let's think about this, okay? I need to figure out the height of each rectangle, okay? The height of each rectangle. How would I figure out the height of each rectangle? If I'm doing the upper rectangles, okay? This is specific to the uppers. We could do the lowers, but it's got to be the y-coordinate, right? So to get a y-coordinate, I've got to evaluate my function at a specific value, right? So I'm not going to evaluate it at 1. Where does the first rectangle end? Well, in this case, 2. What about if it's up here, each one is 3 over n wide, right? So what would be the x-coordinate that I need to evaluate this for? How wide is each one? 3 over n. So I need to do 1 plus 3 over n, right? Now, that's only going to give me how tall the first rectangle is, right? How would I get the next one? How tall the next one is? What? Okay, I could do 2 plus 3 over n if I'm starting here at 2, but I got to start from a 1 plus 3 over n and do another plus 3 over n, right? And then to get to the next one, I've got to do another plus 3 over n. So that sounds like we're doing a sequence, yeah. All right, so here's what I'm going to do. I'm going to put this I in here. And that's going to be our counter. We're going to do a sequence where we have I going from 1 to n. All right? So for I equals 1 to n, we're going to use f of 1 plus 3 times whatever the I is over n. Okay? This is for the height. All right? So now, you guys know the area of a rectangle, right? The area of a rectangle, length times width, or since we're using base times height, just to make sure we know which one's sideways or which one's up and down. Okay? In this case, the base is 3 over n. We're going to multiply that by f of 1 plus 3i over n. Okay? But I don't want the area of just one rectangle. What do I want to do with all of them?
Sum of the area.
I want to get the sum of the areas. So, here's where we're going to use the sum. All right? I need to get my... since my pen isn't working here. Okay, so I want to get area of all the rectangles. Okay, I want the sum of all of the base times the heights, right? So I need to do, I'll get my sum from I equals 1 to n of all of this. Okay? So here we'll write in our n, and I'll make that up here. Okay. All right, we'll do that, and then we need a I equals 1. All right, and we need the sum of this, right? So let's make our sum. All right. So there is the area of all of the rectangles combined. Okay? The base 3 over n times the height f of 1 plus 3i over n. We're doing that from the first rectangle all the way up to the nth rectangle. And then what did we say we needed to do with this? What were we going to do with the number of rectangles? Yeah, make it unlimited. We want n to approach infinity. Okay? So, look at what we have here. I want to explain this. We got the 3 by taking 4 minus 1. The 4 was the right-hand side of our interval. The 1 was the left-hand side of our interval. Okay? So let's say this right here is a b. Okay? We're going to make b the right-hand side of our interval. That's just a common thing that we do. A is the left-hand side of the interval. So we could rewrite this as b minus a. Okay? So the base of each rectangle, we could say, instead of being 4 minus 1 over n, we could say it's b minus a over n, right?
Yeah.
So, and then for the height, it's not going to be 1 plus 3i over n.
Wait, what's b minus a over n? The base of each rectangle?
It's going to be the base of each rectangle. And here, if we're putting it in general in terms of the b and the a, we would have f equals 1 was the a, right? Plus b minus a I over n. Okay?
That's the height of each rectangle?
That's going to be the height of each rectangle.
Okay.
All right? Now, you can kind of see where this is going here. We're still taking the sum from I equals 1 to n, but now instead of this, we have b minus a over n, and instead of being times this, it's times this whole expression. And that's where we get this definition for the integral. If we're going across an interval from a to b, we're taking the limit as the number of rectangles approaches infinity. We're taking the sum from I equals 1 to n of b minus a over n, that's the width, or the base, times the height, f of a plus b minus a over n times I, and that's for the interval from a to b.
Wait, I don't understand why the limit from n to infinity is in front of those things.
Because we want to make the number of rectangles approach infinity, so that we're minimizing how much of that extra stuff we're getting, right? Now, what we just derived is the entire concept behind the integral. Okay? We just derived the integral. Because the area under a curve can be given when we take in the limit. We're not approximating anymore, are we? We're finding the exact, because our sum of the rectangles is going to approach the actual area under that curve as n approaches infinity. Okay? And this notation here, or this definition, we can sum up in this notation right here. The definite integral. What we were just looking at here, the area under a curve from A to B, we can identify as the definite integral. Okay? The definite integral of f of x from A to B is written as A equals this elongated s. All right? That's what the integral symbol is an elongated s for a sum, because we're summing up all the areas, right? Okay? And it's the integral from A to B. Now notice here the A is on the bottom, the B is on the top. You always put the left-hand bound, the lower value of x on the bottom, the higher value of x on the top. So B is on the top. Okay? And then it's of f of x dx. Now notice here the dx. That means with respect to x. That tells us what variable we're integrating with respect to. Just like you guys were differentiating using dy dx, the derivative of y with respect to x, here we're integrating f of x with respect to x. Okay?
I don't understand that.
So that dx is the same thing as when we wrote dy dx. We were simply identifying what variable we're taking the derivative with respect to.
So,
Okay?
so instead of dy dx, it's fx dx.
Yeah. Because remember, remember dy was just telling us we're taking the derivative of a function y and then with respect to x. That's what the dx stands for. Okay? Here, we're integrating f of x with respect to x. Okay? Now, that may not seem that significant, partly because when we did derivatives, we never did what's called implicit differentiation, where you can take the derivative with respect to x, but you've got y's and r's and other stuff in there. Okay, that was beyond the scope of our study. This would be a lot more significant to you if we had done all of that. Just understand that you always put the dx at the end, or the d, whatever you're taking the integral with respect to. Okay?
Why do you put the B on top?
What?
The B on top? Something about
The right-hand bound. Your interval, notice here, the interval for from A to B. Okay? So A is the lower value, it goes on the bottom. B is the higher value, so it goes on the top. Okay? If you mix them up, you're going to get the opposite of the answer you should get. You're going to get a negative area. Okay?
So it's under the
There's a couple ways you can handle it, but that is one way to do it. This right here will give us the definite integral will give us the area as long as we're all above the x-axis. If we cross over under the x-axis, we're going to have to do a little bit with it to be able to get the total area, and unless we just want the net area. The net area would be like the positive area minus the negative area, and it's just balance out to how much. But and in some cases that might be helpful, but the total area will be useful as well. Okay? Now, I want to use this process that we talked about here, and I want to actually run through one like it, and I'm going to give you another one like it to practice on your own. Okay? What I want to do here, this is page 444, number 1. We're going to consider the area between the line y equals x and the x-axis from x equals 0 to x equals 1. All right? So we've got a line, and we're going to find the area from 0 to 1. So here's our 1. Okay? What happened to my 1? Here's our 1. Okay? Now, obviously, what shape am I going to get if I go from 0 to 1 and I have this line right here? I got a triangle. Okay? So, obviously, we could just go ahead and find the area of this triangle, right? How long is this side right here? 1. How long is this side down here? 1. So what should the area end up being? 1/2. Okay? So, area equals 1 times 1 divided by 2, base times height divided by 2. So we know the area should end up being 1/2, just based on the fact that this is a triangle. But let's go ahead and use our rectangles with an easy one that we're going to be able to figure out pretty easily. So it says divide the interval into 5 strips of equal width. Okay, so we'll try to do this. We'll go to there. Let's see, 1, 2, 3, 4, 5. Those are about even. Okay? Now, if we did that, how wide is each one? What?
How many are there?
There's 5.
One.
Yeah, 0.2 or 1/5. Okay? All right, so We know they're 0.2 apart. Okay, which means that, what's the x-coordinate of the second one? Okay, and this one? 0.6, 0.8, and then we're over here at 1. Okay? So, we have all of our x-coordinates. So now we need to decide, all right, we need to do upper rectangles first, okay? So we're going to do upper rectangles. I'll do these ones. Excuse me. Let's do those ones in blue. Okay? So that means I'm going to come here. I'll make them somewhat thin here. All right, so here's one rectangle. Here's another rectangle. Here's another rectangle. Okay, and what do we need to do with each of these rectangles? Find the area, okay? So in order to find the area, we know the x-coordinates, right? We know the width. The width is 0.2 on all of these, okay? So if the width is 0.2, we got to find the height. What's the height of this one? 0.2, okay? So what's the area of this rectangle right here? What's the base? 0.2. What's the height? 0.2. So what's base times height?
0.04.
0.04. There we go. 0.04. So that's this rectangle right here. Okay? So that's 0.04. How about this rectangle right here? What's the base? 0.2. And this is 0.4. And what's the area? 0.08. Okay. All right, so let's put that in there. We got 0.08. Okay. So how about our next one? 0.12. 0.2 times 0.6. 0.12. Okay. How about the next one? 0.16. And finally, 0.2 times 1 would be 0.2. Okay? So now we can add all of those up. And what do we get? With the uppers, what do we get? What is it? No. No. If we add all these up, what do we get? Come on, guys. Engage. What'd you say? 0.6, okay? So our uppers are giving us the 0.6, okay? Now the lowers, we can do the lowers as well, all right? I'm not going to run through the entire process here, but let's take a look at these lower ones. We're going to make, again, we're going to make the rectangles, but we're going to use the left side or the lower side of each one. So guess what? What's the height of this one? This first rectangle? 0. Okay. Here's our first rectangle right there. Because the left side of it's 0. See right here, the left side of this rectangle is 0, so I'm using, what?
Because you can't pass the line.
Yeah, it goes down to the x-axis. Now for this one, we're going up here to the left side.
Excuse interruption. Alec Lawson, please come to the high school office.
All right.
Alec Lawson,
Yes, he's here.
can you please ask him to come to the high school office?
Yes, he's on his way.
Thank you.
Can you make the assumption that the lower is going to give you 0.4 or no? No, fine.
Well, in this case, it does end up being 0.4, okay? That's why we're not going to run through all this. Here's the thing, guys. Since this is a straight line we're doing this with, okay? Since this is a straight line we're doing this with, when we do the lowers and the uppers, they are going to actually average out to exactly what the area is, okay? So, I'm not going to go through this whole thing again, but notice on the lowers here, please stop talking, all right? Given this, we should not be talking, all right, unless it's to answer a question. So, for our lowers, we have 0 plus, in this case, 0.04, plus 0.08, plus 0.12, plus 0.16, okay? Now notice here, we got a lot of the same areas for the rectangles, but they were all kind of shifted over one. All right, so we had the 0 to start with, and we never had this 0.2 at the end. All right, but this all ends up equaling 0.4, okay? And because we were dealing with a line, when you do average the uppers and lowers, you got exactly what the area should have been, okay? It's not always going to be exact, but it will actually be somewhat close, okay? So, any questions on how we could use area under a curve with rectangles?
Does it matter what kind of function it is, or if that's linear, or like what if it's parabolic?
If it's not linear, then when you average these, you won't get exactly the area.
Because you said area under a curve, but like that's not a curve.
Well, yeah, it's just I mean, theoretically, any function is a curve. It's just,
Okay, but it all works the same no matter what function.
yep. So, one of the ones I want you guys to try, I gave you 2 problems for Thursday. One is to do this, okay? Sketch y equals square root of x from 0 to 1. Shade the area from 0 to 1. Then do upper and lower rectangles for 5 rectangles and for 10 rectangles. And then see if you can't approximate that to 2 significant figures. Okay?